Oh boy. Hey, Science 20s. Today we're going to be talking about radiation. Ooh, exciting. I don't know if you've seen, there's a documentary on HBO called Chernobyl. It was about the nuclear meltdown in the Chernobyl power plant, and it was kind of about the cover up that happened and how dangerous the radiation is. But in geology, we can use radiation to help us out. Marie Curie was a scientist who studied radiation. She actually has an element on the periodic table named after her. And in the link to today's lesson, there's a little 4-minute video about who Marie Curie is. On my desk, not behind my desk, I have actually a little magnet of her. She was one of the big inspiration to me why I was so interested in chemistry. I read about her life and how much she achieved and overcame. And sadly, because she studied radiation and they didn't know the effects of it at the time, that's what she died of. And her remains are actually in a lead-lined coffin so they don't poison people that are around. So that's how even in death, she's super badass. Okay. Now, what we're going to be using radiation about is that everything that's radioactive has an intensity that it's emitting radiation. And we're not going to get into what the physics of what that is. That's left to Science 30. But that intensity gets cut in half at absolutely perfect intervals of time. And this is something called a half-life. So a half-life is, maybe you heard it from a video game, maybe it's been in science fiction, but every time you check something at a certain timeline, half of its intensity is gone. Some things have very short half-lives. So half of the intensity is gone in a few seconds. Some things like uranium have half-lives of thousands or millions of years. Now, a parent nucleotide is the original substance. And that parent nucleotide is something that is the most radioactive and it's unstable. On page 8 of your data booklet, so if you have your data booklet, and you're going to need it for this part here, this next little part, on page 8 of your data booklet, there is some really interesting stuff about radiation. And we are going to be using the elements for radioactive dating way at the bottom. So a parent nucleotide is something like carbon-14. We talked in chemistry about what that 14 means. It's the addition of the protons and neutrons that make up that element. And carbon-14 is not typical carbon. It's really unstable. And carbon-14 decays, which means that it changes into nitrogen 14. So carbon has 6 protons and nitrogen has 7. So over time, the carbon forms something that's a little bit more stable. And in Science 30, we talk about what that is. So kind of what happened here is a neutron turned into a proton to keep the mass number the same. So we'll just say this is the original element. There's something called a daughter nucleotide, and the daughter nucleotide, is what it decays into. So it's really hard to memorize this, so that's why on page 8 it gives you a bunch. So for example, potassium 40 is a parent, and it decays, its final decay nucleotide is argon 40. So if you look on page 8, there's the parent, and the final decay nucleotide is daughter. Now we can use this to figure out how old stuff is. So really quick, what's radiation? It's energy lost by unstable elements. There's different types of radiation. There's alpha radiation, and there's beta radiation. There's lots of different types. We're not going to get into that. Just think of it as energy that an element is losing to become more stable. Okay. Oh, look at that. The definition was already there. Okay, why is this so important? Well, every element can be measured, that energy, and every element will lose energy at a different rate. And you can measure that. And if you can measure it, you can figure out how old something is. It's very cool. And does this ever change? And the answer is no, not really. This radioactive decay is really accurate. No, answer no. So why are half-lives important? Well, we're going to talk about what a half-life is, just to give you an idea what a half-life is, because it's kind of hard to wrap your head around. So let's say you had 100% intensity of an element. Say we're going to use carbon-14. Okay, carbon-14. When half of the intensity is gone, that is one half-life. When half of that is gone again, that's a second half-life, because this is one half-life, two half-lives. And then what's half of 25? What's half of 25? It's like 12.5%. That's another half-life, or three half-lives total. So if you go from 100% carbon-14 to 12.5% carbon-14, that is 1, 2, 3 half-lives. And what's interesting is that you may have way over here 12.5% carbon-14, but that means all of the other stuff, the 87.5% of my math correct, the rest of the stuff is now the daughter nucleotide, which is the nitrogen-14. And these half-lives have certain amount of time periods that it takes to occur. If you check page 8, every half-life for carbon-14, so every time it gets cut in half, that takes 5.3 times 10 to the 3 years, or 5,330 years. So it takes that amount of time to go from 100% to 50, 5,330 years. It takes another 5,330 years to go from 50 to 25, and it takes another 5,330 years to go from there. So guess what? If you add these all up, or you times them by the half-life, we can figure out how old stuff is. Okay. So that's what this is going on. This takes a long time for carbon-14 to turn into nitrogen-14. This is the idea, right? So what we're going to talk about is how do we actually calculate this in a couple examples. So if you have 25% left, what you can quickly do is you can go, okay, 100 goes to 50, that's one half-life. 50 goes to 25, that's two half-lives. Okay. So if you have 25% of a substance left, it's gone through two half-lives. Okay. Now, if you have two half-lives, you can times that by the half-life years for carbon-14. 5.73 times 10 to the 3, and we're going to times that by the two half-lives. So I'm just going to grab my calculator real quick. So 5.73 times 10 to the 3, or remember, if you don't like that, you could write it out. That's 1, 2, 3, right? 5,730. Okay, and we times that by 2, we get 11460 years. So that's how old a sample of carbon-14 is if it has 25% intensity left. Now, why is this important? Well, the thing about fossils is that everything in a fossil that used to be alive is now gone. It's a rock. And most fossils, actually all fossils, aren't radioactive. So it's not like you can take a dinosaur skull and then point a Geiger counter at it and figure out how much radiation it has. It doesn't work that way. But we can use stratigraphy from yesterday to figure this out, to get an approximate age. So, for example, if we want to figure out how old these trilobites are, which are these creepy, crawly little bugs that ruled the Earth for millions of years, we would find a radioactive rock in the same layer as the trilobites. So, this rock that was found had 12.5% rubidium left. Okay, so how many half-lives is that to get to 12.5? 100 to 50 to 25 to 12.5, right? Each of these I'm cutting it in half, right? 1, 2, 3. This has gone through 3 half-lives. So I checked table 8, and I'm like, okay, rubidium 87 has a half-life of 4.88 times 10 to the 10. And I'm going to that's one half-life, and I'm times that by 3. So we're going to get a huge number. So these trilobites are hecka old. 4.88 times 10 to the 10, times that by 3, I get 1.464 times 10 to the 11. So we know that rock is that age. So stuff that's found in the same layer should be around the same age. Now, it's an estimate, right? Because that, maybe lava had moved that trilobite up a bit, or maybe the strata is going back down into the earth. So that's why paleontologists have to give a range of when animals and dinosaurs used to live. Okay. So let's say we got around 12% uranium-238 left. How old is that? Well, we just figured out in this last question that around 12% is 1, 2, 3 half-lives. So that's 3 half-lives. We check table 8 in our book for uranium-238, and we find that uranium-238 is 4.47 times 10 to the 9. I'm going to times that by 3 half-lives, and that gives me how old the sample with that amount of uranium is in it. 4.47 times 10 to the 9 times 3. Okay, I get 1.341 times 10 to the 10 years. So super, super, super old. Okay. All right, so that's today's lesson on radioactive dating. Now, you guys are going to be working on an assignment to hand in through Floop. That's going to be due on Monday. So there'll be a bunch of questions on this and some questions that we've already covered on Monday and Tuesday. Okay? All right. Thanks, guys.